Let's get started. Okay, let's get started. So first, a few announcements. So it turns out that more than 100 students did not follow the naming conventions in the first assignment. So that means that our scripts have broken, and we're going to have to manually look at lots of them, which means there are 100 of you who are going to lose some points. But it's also going to take us longer for us to grade everything. So please follow the naming conventions. Don't name it whatever you want, because then we'll have to go manually look in to see what you've named things and sort of compile, and the TA will get angry. She might take off a few points, or she will take off a few points. So please follow whatever conventions, naming conventions there are. In general, if you have any issue with grading, contact Lena. So Lena Reed is taking care of all the grading, and she is the one to contact if you have any issues with your grade, or if you make a submission and some of it works and some of it doesn't. Say you're not able to make your code, like someone had this problem, like the code works, but then the make file is not working for some reason. Contact Lena and let her know. Submit whatever you have to through Git, and then contact Lena and let her know. And that way she has a record of what the issues are, and then I'll sit with her and sort of go through all these cases to decide how to grade them. For the next assignment, I'll give you, yes? Where is her contact? Where do you think it would be? Exactly. It's on the website. So I'll give you more time for the next assignment. The next assignment will actually be on linked lists. So it will be building on the code that you have. I will release a solution for homework 2 in 2 days. And that way you can build on that, and I'll give you more time for it. Any questions? The next lab, I will put it out today or tomorrow, and I'll give you a couple weeks. I'll give you more time for this lab because it's on C, and I'm going to be discussing most of these things this week. A question, hand over there, yeah.
In the description of the homework, it says that our thing shouldn't take a command argument.
I'm sorry, say it again?
It says our homework 2 shouldn't take an argument, so should we have it like directly find an input.txt file?
Yes, yes. So we will run it with our own input.txt file. Right, yeah. Hand here, yeah? So yeah, I should have clarified that. Do not worry about a piece being outside the board. So assume that the input will be correct, and you don't have to worry about error handling on the input, and no piece will be outside the board. Yeah. Yes, it's type column and row. I don't think it really affects your code if you were to switch everything, because your search would still be the same. The attacking doesn't change whether you switch rows or columns, except for maybe pawns where it does matter. But yeah, so I don't know. The way I like to think of it is it's almost like x coordinate and y coordinate. That's usually how you specify something. And x coordinate is like the column, and the y coordinate is the row. Make sense? Sort of? Yeah? The homework does not take a command line argument. That's right. So because input.txt, you have to just you just read input.txt and assume that there will be an input.txt in the folder. Right? So that, how do you access a text file in the folder? That's lab 2. Lab 2 tells you how to sort of access files. Question? Okay. So today, I'm going to be doing, unfortunately, I know of no other way to do this. I'm going to switch between the laptop and the document camera. It's a bit annoying, but I'm not able to project both of them simultaneously. And the reason for that is, hang on. Today we are going to do pointers for this week, we'll probably be doing stuff related to pointers. You actually don't need to know any of this for the programming assignments, because the programming assignments are in Java, pointers are in C or C++. You will need to know some of this for the lab, for the next maybe 1 or 2 labs. Question? Midterm, we'll talk about the midterm later. But understanding pointers is sort of extremely fundamental to computer science. It's also commonly thought of as a drop-off point for students, that they get confused with pointers, so please pay attention. It's really important because it starts actually telling you how computers function. You start learning more and more. So you can think of, there are various levels of abstraction of understanding computers. One is you just understand at the level of, oh, I have this app, I press this button, something happens. Then you start thinking of it in terms of code, like you write code and then you understand it. The next is to actually think of what happens sort of at the hardware level when you run code. And pointers kind of give you a link between sort of code and software and how it interacts with hardware. And we discussed some of this. When we were discussing references in Java. But as you'll see, I'll give you lots of examples, lots of code snippets, which I'll actually compile and run to kind of show you how pointers behave. So as we discussed, memory is best thought of like this linear chunk of spaces where, let's say, each block is 1 byte. That's 8 bits. Right? So you have like this long piece of memory in blocks, and each block is a single byte. And each block has an address, right? So this is the address 0, this is the block 1, block 2, so on and so forth, and this may be block, 420 or whatever, so on and so forth. So you have all these blocks, and when you write something like int foo in your code, your compiler has to go and find some block of memory where it's going to write foo. So you'll see that actually an int is 4 bytes. And I'll actually show you a command that will show that to you. So when your compiler runs int foo, it goes and it picks up 4 bytes and says this is foo. Yes? Sure, we'll get to that. The sizes of the primitive types. But so an int is 4 bytes. Now C and C++ have a special type of variable that actually stores addresses. So what you have is you can define something called int star ptr. This is a variable that stores the address of an int. So in Java, as we discussed, we don't really have this distinction, but in C, it sort of makes this explicit. Int foo, that's an int, but int star ptr is a special kind of variable that stores the address of an int, and this is called a pointer. And it's a pointer to an int. So wasn't that scary, was it? Okay. So you can also define something like float star. I'll say fptr. This would be a pointer to a float. But all pointers are just storing addresses, right? So the address of something here, assuming that this was, say this was block 50, let's say it starts 50, then the address of foo is 50. Yeah? No, sorry, in this? No, you can, you can call this whatever you want. You just have to put the star. The star is what makes it a pointer. A pointer. So if you wanted to declare more, you do something like int star ptr1 star ptr2. In general, people recommend that different people have different conventions. They would say put pointers on separate lines, like every single pointer. Some people put them in the same line, but you should do this, not int star ptr1 ptr2. You have to do this, not this. Unfortunately, this will also compile. So the problem with C is that it compiles anything. You give it anything and it says, yeah, sure, I'll run it. And then you spend like days debugging it. So in this case, what it's actually going to do is it's going to make ptr1 a pointer and ptr2 a normal int. Because it says, oh, the star goes over there, but there's no star there, so that's a normal int. So it can be quite confusing. Yes? How do you know which int it points to? So right now, when you do int star ptr, you just have a variable that can store a location. It doesn't have anything, or it might have some garbage in it. It's a 4 or 8 byte address depending on your machine, depending on how much machine is. If it's a 64-bit machine, then it would be 8. Otherwise, it would be 4. It's a 32-bit machine. Yeah?
So if a pointer is just an address, how come the type has to be specified for the pointer if all addresses would be?
Good question. So we're going to talk a lot about why you need to specify. Why do you need to specify a type? Because you're right. Actually, and this will come up that PTR and FPTR are both just addresses, but the compiler will interpret them in very different ways. And you'll see a lot of examples of that. And this indeed is the source of like multiple errors in C. Okay. So what you now have is this operator that's called this is called the address operator, also called the referencing operator. The way to think of it is address of foo is or ampersand of foo is the location or the address of foo. Right? So what you can do is something like this. Let's just, sorry, maybe I'll leave that there. So we have int foo, and then we have int star ptr. You would say ptr is equal to ampersand foo, which means ptr stores the address of foo. Right? That's what this command means. To stress, you don't really have an equivalent command in Java. Right? So you don't have variables that are dedicated to storing addresses, although implicitly in Java, when you say a variable for a class, it's basically a reference. It is really a pointer, but you don't get to manipulate the pointers in the way that you'll see here. So questions? Yes?
Can you assign the address of a variable to something that's not a pointer?
No, the compiler will probably throw an error. Again, it might actually, I think it would throw an error. Like when you say ampersand, but okay, I'm going to show you some code, and then maybe we'll talk about that further. Yes? How will you handle what? Strings. Yeah, so strings are basically arrays of characters. So especially in C, it'll be really explicit. It's just you have to allocate some array of characters, and then the string library probably does some dynamic allocation. Yes? How do you point to linked lists? Okay, let's not even go to linked lists yet. Let's just talk about ints. Yeah? The star after the, yeah. Yeah, so actually, you can also do this. So C is in, so whether you put the space over there or over there doesn't matter. C is crazy, right? So there are all these little syntax things that I don't know, and you Google for it, and someone says, oh, you do this, and it gives you the same thing. So, and there are flame wars as to whether you should put the space here or there. But yeah, so you know how these things work. But be careful. This is 2 pointers. This is not 2 pointers. The natural thing is to think, oh, int star is a type, so I write the type, and then I write a bunch of variables. No, it doesn't work that way. Yeah? Here? You wouldn't want to put any parentheses over here. Yeah, you wouldn't put parentheses here. Okay, so wait. So now let's actually look at some code. And frankly, this is the easiest way to learn about pointers, is to just write a bunch of code snippets. Otherwise, okay, so let's look at, can everyone read this? Should I increase the font? Make it a little bigger. That help? Okay. So what have I done here? I've defined three variables, foo and bar, which are ints, and a character C. I set foo is equal to 42, bar is equal to 7, and C is, the character C is, or rather C is the character A. Now I can say print the address of foo, and you'll see what I did was I just put ampersand foo, and I've cast it as an unsigned int. Just think of this as an int, like I'm just doing %d. Don't worry about the u. And I can say the address of bar and the address of C. Okay. So let me compile this. This was it threw a bunch of warnings. Was not entirely happy because it says the format specific type is unsigned int, but the argument is of type int star. So it did detect that there was something funny. It compiled. It just threw warnings, right? And so now let me run this. Here, I get the address of foo, the address of bar, and the address of C. So the address of foo is 1457961692. That's the actual address in memory, right? And the address of bar is 88, right? So the difference between 88 and 92 is 4. And then the address of C is yada, 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 87. So what it did was, ignoring the 1456, at address 92, it says, I'm going to put foo. Now, the weird thing is it's actually putting stuff backwards in memory, right? And this is something related to x86 architecture. So if you run this in a different machine or somewhere else, you might get different. It could be different. There's no reason why it has to actually place these things next to each other, but it just so it did. So and note that bar is actually going to be the reason. So why is bar placed at 88 and not 91? It's 4 bytes, right? So it needs 4 bytes, which are separate from the bytes for foo, and so it puts it in 88. A character is a single byte, which is why it puts it at 87. It's really interesting. Like this simple piece of code starts telling you a lot about actually architecture, right? Which is why I said pointers are really important to know so that you understand how code interacts with hardware, with memory. Does make sense? Nothing fancy here yet. So at address 92, you have foo. At address 88, you have bar. And at address 87, you have a single character C. Okay, questions? Yeah. What is unsigned? An unsigned int is just an int that doesn't take negative values, because memory can never be negative. I mean, this is in general not what I did here is like something like it shouldn't be done because it's throwing warnings, because it's saying that look, this thing is a pointer. You really shouldn't be treating it as an int, but you can if you want to. So I'll just go ahead and compile it, and it compiles. Okay. So let's get rid of that. Now you can do the same thing for a structure. You can also get the address of a structure. So I define a structure student. It has 3 fields: an int, ID, a character, which is the major, and an int, which is the year. Okay? And I define foo, bar, a character C, and a student S. And now I can actually go and say, what is the address of the student, which is a structure? Make sense? So this was, again, it threw a bunch of warnings, but it compiled, and it does this. So let's look at these numbers. So another question, actually, let's go back to the old one. Let's just do this one. So foo is at 96, bar is at 92, C, which is a character, is at 91, and student S is at 76. Right? So it allocated a lot more memory for student, because student has 3 fields in it. If I run the code again, will I get the same answers or not? What happens? If I run the code again, will I get the same output or not? Yeah? Okay, they might not be the same numbers. Yeah?
C doesn't do garbage collection automatically, so they're still there, right, until you actively include them.
Well, the code just finished. The code ran and it just finished. I keep getting different numbers, right? But the distance is still the same. And the reason I get different numbers is because this code is now interacting with the operating system, and whenever it gets is int foo, it says give me 4 bytes for int, and the operating system finds something and gives it. Right? So every time you run, you get different answers. So this is, again, bad code, right? Something that gives you a different output every time you run is dangerous code. But there you have it. Okay, question.
Will foo still be at the same, will there still be a foo at the first address? Or will foo?
I mean, all bets are off at this point, right? You ran the code, maybe something is written there, maybe some other process goes and takes it up. You have no idea. Yes? Why is the student, is it not bits, bytes? 15 bytes. Good question. I'll come to that. Good question. Yeah?
If you were to rearrange the way you declare variables, like if you set struct student C above int foo bar, would C just automatically allocate space before it allocates space for foo bar?
Why don't we do that? So if I understand correctly, what you're saying is, I'm going to move it over there. And then now I compile and run. Okay, let's do that. What happened? It actually allocated student in the beginning. So remember, it's actually allocating sort of in decreasing order of memory address. Strangely enough, right? You would think it would do it in increasing order, but it's doing it decreasing order. So it actually allocated student first at 24, then it allocated foo at 20, then bar at 16, and that at 15. So it's actually doing it in the order in which it's there in the code. Right? So does that answer your question? Yeah. It's a good question. Right? So the order in which you put things does change the order in which, and again, the compiler doesn't have to do it in order. It can put it anywhere. But what probably happens is as soon as the program runs, the operating system blocks off a chunk of memory for this program and starts filling it up with the variables. That's probably what is happening. Okay? All right. Good? So far, so good? Yeah, question? No, when the program is done, that's it. That memory is freed. Right? Because the program, it runs for like a millisecond. Sorry? The second time it runs? Yeah, the second time it runs, it just goes somewhere else. The operating system, it might give it the same thing. It could do anything. The point is, when this program is run, the compiler says, I need 4 blocks of memory for student S, foo, bar, and C. It goes, it finds something. The program finishes, then that memory is freed. And the next time it runs it again, it gets 4 more. Okay. Let's do this one. This is interesting. Okay. Let me just clear this so that you can see what's going on. All right. So again, I have student, which is an int, a character in a year. I have foo and bar, character C, student S. I've just set these, although we don't need that right now. So the address of foo, bar, and C as before. Now here's and the address of S. Here's what is interesting. I can actually ask for, give me the address of the ID in student. So let me actually make this a little smaller. Can you guys still read this? Still good? Yeah? It's too bright? Maybe I'll just turn the lights off. Which one is it? Does that help? No? I don't even know which one that is. You know what I can do is I can just switch the windows then. Wait. What do you mean no available windows? Okay. No. Okay. Is this better? No? Whatever, it's fine. I'm reading it out anyway, right? So what do you have here? So you have the address of student. Then you can actually get the address of s.id. Remember, student has 3 fields, ID, major, and year, right? So you can get the address of a specific field within student. Does that make sense? So what do you think the address of s.id is with respect to the address of S? Right, so you have s.id, and then you have S. Yeah? It's inside S. It's inside, sorry, say that again? It is inside the allocated memory. So let's see what happens. Lots of warnings, but it compiles. Okay. the address of student and the address of student.id are the same. The address of the major is more, and the address of the year is even more. But all of that is all less than foo, bar, and c, which were allocated initially. So, I mean, maybe I'll draw on this board and we'll see if you can. So what happens is student, so the struct, student has what? It has an int, ID, a character which is major, and an int which was a year, right? So the way it works is it says I blocked off some bytes, and it seems like it's 15, and we'll get to that, starting at 80 for student. It's blocked off something for student. Student has 3 fields: ID, major, and year. So it first puts the ID right here. Then it puts the major here. So this is going to be ID, this is major, and this is year. And the starting address of this entire block is the address of student. But it also happens to be the address of student.id. Right? That's why they're the same. Then you have s.major, which is now at 84. I know this is interesting. And then you have s.year, which starts at 88. Yeah. It's not an array. It's just a block of memory. Exactly. Exactly. Yes, good. So array is not the, I mean, yeah, so it's not an array, but the way to think of it is major should just be 1 character. That's all it needs. But it's giving it like 4 bytes. Do you see any pattern between these numbers? They're also divisible by 4. All of these, like 0, 0, 96, not 95, 80, 84, 88 are divisible by 4. The compiler or the operating system likes to have addresses that are divisible by 4 because it actually optimizes things. And for that reason, it puts in this extra space over here, which is not going to be used, because even though major, so I wouldn't say it's an array, but rather it's aligned to memory. It's aligned to sort of blocks of memory. Yeah? I am not sure. Maybe is that so? I guess in this case these are all primitive types, so I'd have to maybe put a double and then see. We could try that. Let's see. So which one was this? Yeah, like so. Frankly I don't know the answer to the top of my head for these, so I would. Oops. Board. I do it here. Yes. So we could basically make this in a long. Right? Make that longer. So a long would be 8 bytes. And then we could compile and see what we get. No, it did the same thing, right? S.id and S are the same. Major is again 4 bytes ahead, and year is another 4 bytes ahead. But you can see that the difference between the address of S and address of C is much more, because now it's actually allocated along. This make sense? Yeah? Right. So when you want a character, it just does 1 byte. What it might do is then if you allocate another variable after that, it'll then align that to 4. Right? So I'm not sure yeah, that's likely what will happen. But at that point, since you just wanted 1 byte, it just went and said, okay, here's 1 byte. Again, a lot of these are compiler dependent. It also depends on the operating system. It depends on the hardware. Maybe if you ran this on an Android machine, on an iPhone, maybe you'll get something else. So, but it's really interesting, though, just looking at these programs to understand what's happening under the hood. And again, note that if I run this over and over again, I start getting different numbers. It's allocating at different places. OK? Yes? If you have an ID that's longer than 4 bytes, so int will overflow. So if you put, so int, the maximum possible int value is 2 to the power 32, or maybe 2 to the power 31, which is, let's say, it's about 1 billion. Yeah. So if you were to put 1 trillion into an int, you will basically get what's called overflow, and you get some other strange number. It does some weird things with the bits. So if you want to store a sufficiently large number, you have to get a long. And if you want something that's even longer, then you should probably use a float and give up the precision. So this is, again, an extremely common error that happens, which is you might think, oh, in 2 to the power 32 is long enough. But for example, like at Twitter, they enforce everyone to use longs because they do have like 1 billion IDs. And so it is possible that you get overflow. And so they will always enforce using longs, even though some of the numbers are not that big. Yeah?
So with overflow, does that mean that it would write on to the next space after it and it would only use 4 bytes? Or
It will not write anything out of that. Okay. So it'll actually, when it tries to copy something in here, it'll actually not copy everything. Yeah, so when you touch s.id, no matter what you do, you'll never touch any other location of memory. Sorry, say that again? So in general, if you have, let's say, int foo, and you assign some insanely large number to foo, that command will never touch any memory block other than foo. Right? It's not going to sort of pad stuff outside. Yeah? Why is the difference between s, say that again? S dot major, you mean? So,
student and character, why is it like not divisible by 4? Shouldn't the difference be divisible by 4?
which difference? Say that again. Oh, between year and C?
Yeah.
Because C happened to basically start at a non-divisible by 4 location because it wanted 1 byte. I mean, this is eventually going to waste like 3 bytes at various places. And that's to make the addressing more efficient. OK. Now let me switch back to the document camera, and we'll come back to more code. So what I will do is actually all these programs that I've shown you, I'll actually put them on the course website, so you can download them yourself, and then you can modify them to see, just to experiment. So right now you saw this operator, the ampersand operator, which gives you the location. And so what is really important is the opposite operator, called the star. And what this does is it dereferences. So star PTR is the content of PTR. Or another way of thinking of this is, so you had foo, 4 bytes. So ampersand foo, let's say foo started at 42. So ampersand foo is 42. And let's say foo actually stores the value 1000. But star of 42 is 1000. Does that make sense? So, or I think the way, let me write this more formally. So you have int foo, int star ptr. So what you would say is ptr is equal to ampersand foo. Now if you do star ptr, you will get the int that is at ptr. Right? So ptr is a pointer to an int. Star ptr, okay, so this is just, don't get confused between these two stars. This is a declaration. But these are commands. So you can do something like print, or technically printf, and I will show you a snippet of code that does that. But what this means is, this is the int stored at ptr. So someone had some question as to why should you have different kinds of pointers, and it's for this reason. When you do a dereference, when you say star of ptr, it has to go find the contents at ptr and say, what is this? Well, the type tells you it's an int, so interpret it as an int. Does this make sense? So the star operator gives you the content, or I should say content not of ptr, but rather at ptr. Right? So ampersand and star are like the opposites of each other. Ampersand says, for a variable, what is the location? And star says, for a location, what's stored there? So say it again. The star and ampersand are not the same symbol. I don't see how you confuse those. I mean, my handwriting is bad, but not that bad. Yeah.
So ptr has a value of character, right?
What you mean? What is stored at PTR? It could be anything.
So when you declare ptr, you put car, star.
Yes. Yes, you can define, yeah, I'll show you some code. You can define pointers to different types. And then you can define a pointer to a structure. Yeah? Yeah, so star means you're getting the content of the int stored at PTR. Right? PTR is a location. Right? This is a location. Now, what are you going to do with locations if you cannot fetch the contents at that location? So star PTR is like saying, again, please don't confuse the star PTR here and the star PTR. This is a declaration of a pointer. This is a dereference. Yeah? Good, yes, it will print out 1000 in this case. And so let me show you as long as you remember this, let me just show you the snippet of code, and I think it should be clear then. Again, pointers are confusing, so, and which is why I think like the way to do it is, again, look at these programs. I mean, I forgot some of this stuff myself, so I just coded it up, see the output, and then it starts coming back to you. So I recommend that you try running these pieces of code to see what you get. Okay, so okay, good. So what have I done? I've created 3 pointers, I have an int foo, bar, and a character c. Now I've created 3 pointers: ptr foo, ptr bar, ptr c. You don't have to write ptr there, right? You can give it whatever name you want. I just did this so that it's sort of clear. Right? So this is just a name. You can do whatever you want with it. And so foo is 42, bar is 7, and c is the character a. Now I said the pointer foo is pointing to foo. Means pointer ptr foo will have the address of foo. Ptr bar will have the address of bar. Ptr c will have the address of c. That's what these commands mean. Right? So far, we've only been printing ampersand foo or ampersand bar. But what you really do in code is you store the location in a pointer variable. Does this make sense? OK, so this, I've just printed out these addresses as before. The compiler won't be happy. But this is the dereference. So I say, what is at ptr foo? And I do star ptr foo. What is at ptr bar? And I do star ptr bar. So let's run this. Again, it threw warnings because of these commands, because it doesn't like me printing pointers. But it will still let me do that. OK, there. So at ptr foo, so at this address, whatever that crazy thing is, you have 42. At this address, you have 7. And at this address, you have A. Right? Because that's what this is doing. Does this make sense now? This is how you dereference a pointer. Yes? Because a pointer is a reference, and you're doing the opposite of referencing. So it's a dereference. Yeah? You can get a pointer to a pointer. And it actually it means something. Yeah, you can keep doing this. You can do pointer to a pointer to a pointer to a pointer. Yeah. Is it possible to what? Is it possible to set a memory address to something you want? Yes. Because star PTR allows you to basically reference what's going on there. So what you can do, for example, over here, let's say star ptr underscore foo is equal to 100, which means at the location ptr foo, put 100. Right? I changed the value now. So does this make sense? So initially, let's see, foo was 42. ptr foo was the pointer to foo. I printed out the contents at ptr foo, and I got 42. Now I can say star ptr foo is equal to 100. What does that mean? It says this is the content at location ptr foo. And I can go ahead and put whatever I want there. I say in that, put the value 100, and now I get 100. So to change a variable, it's enough to have a pointer to that variable. Yes? No. No. So when it actually has not allocated 4 bytes for it. No. So in this case, if you look at ptrc, it's only allocated 1 byte. In the struct, it didn't really allocate this to major. It wasted that space to align. You could. You could. Yes, you could. So because once you get this address, you can say put something at 85. And then you really start mucking with the memory. And a lot of like exploits and buffer overflows are done through this method. Yes?
When you first create the pointer, is it 20 anything, or just like before you do the ampersand?
Uh-huh.
Is it 20 to anything? Or?
We can print it out and see. You mean like right there? So at that point, it probably just has some garbage value in it. But we can see what it does. Oh, initially, okay, so actually, I stand corrected. It initializes at 0. So the initial thing is 0, which is like null. Yeah. No. Yeah, so when you initialize a pointer, I guess it initializes to 0. Yes?
Is foo still 42, like
At the end of this process.
Yeah, but if you printed foo again at the end, is it 100 now?
Okay, what do you think? So now let's go back to this code. So is this question clear? So I'm going to remove this line because it's confusing. Right? So how many people think it's 42 and how many people think it's 100? Raise your hand if you think this is going to print. Remember, foo started at 42. So I'm just, yeah, foo started at 42. I got the address of foo, that's ptr foo. I printed all this stuff. Then I said star ptr foo is equal to 100. What's foo? Yeah? So how many people think it's 100? Okay, good. What happened? Oh, I forgot to. Right. It's 100 because you changed the content at ptr foo, but what ptr foo is pointing to foo. Someone had their hand up over there? Stretching. Huh? Oh, stretching, okay. Yes, you're not stretching.
Can you just increment the pointer to like read through every memory address?
We'll do that. Yeah, you can. That's exactly why pointers are dangerous.
Yeah, but I mean, does a single C program have access to all memory addresses?
No. No, so what you, if you ever access something that you're not supposed to access explicitly, you get a segmentation fault. But that implies that the other person the other program should have protected it well enough for that not to happen. There can happen situations where maybe it just deallocated something and it's not protected, and then actually it could go and look it up. And that's often how a lot of exploits like figure out passwords or something, because something is stored in memory, and then they're like, okay, we're done with that, we deallocate it, and then this C program goes and comes and looks at it through a pointer. Yeah, yes? Why is foo 100? Okay. Okay, so initially we set foo, can you see this? To be 42. Now, ptr foo is that location. I'm just going to use the last two. So that location was 64. Then what we said was star, so remember ptr foo is equal to 64, basically, right? So star ptr foo, this is the content at 64. And this command over here says, go to ptr foo, whatever, so when you do this, so technically ptr foo is sort of pointing to that. So you're saying in the location ptr foo, put the value 100. Right? So it's going and putting 100 there. And so when you say pass by reference, that's often what happens. You pass a pointer to an object or to a struct. Yes?
You talked about in an earlier class about how Java is passed by reference, right? And so does that mean if like you had foo in Java and then another thing like, I don't know, foo2, and you declared foo2 is equal to foo and then changed foo, would it change?
Yes, it would change foo2.
Then how do you usually temp replace them?
So what you would do is usually you would have some sort of copy function that creates a fresh copy of an object. So in like Python, you actually have this thing called deep copy. So you would say make another copy of this. And so you would have to make an explicit copy of the new object. Yes. How much space is allocated for a pointer? 4 bytes to 8 bytes, depending on your machine. Yes? So this is the same as foo equals 100. The old value of foo disappears. Okay? So maybe, I think by now, most of you should be able to answer this question, but there. So look at this. Sorry, I should. Intro 1.c. Okay. Yeah. All right. So again, we have the same setting foo bar c, these pointers. I now equated the pointers. PTR foo is equal to PTR bar. Right? So I set foo to be 42, bar to be 7. Let's ignore c. And so PTR foo is ampersand foo, PTR bar is ampersand bar. So PTR foo has the address of foo, PTR bar is the address of bar. Then I said PTR foo is equal to PTR bar. And now I print star PTR foo and star PTR bar. What's going to be printed? Okay. Are you giving the answer? You are. Wait. So how many people think that this line over here is going to print 42? Raise your hand. How many of you think it's going to be 7? Okay. It's 7. I will just run this for completeness. It's 7, right? Because you equated the pointers. So now PTR foo is actually pointing to bar. Okay? Questions? Yes? Did we lose 42? Interestingly not, because you still have foo. You have the variable foo. Right? So you still have access to foo. But this is a common way in which something called a memory leak happens, where you might lose access. You still have the variable, so you're fine, but if you didn't have the variable lying around, then you would have a problem. Yeah? Okay. You mean that? Okay. Let's do that. What do you think will happen? Will the code compile? Will it crash? Will it run? It's C, it'll compile, right? It might complain. I wouldn't be surprised if it complained. It didn't. It did say that warning, incompatible pointer types. So it warned you that there's something wrong, but it didn't complain. I mean, it didn't prevent you from compiling. And now you get some garbage. Right? So this is one of the biggest problems when you write C programs, is that it compiles and it runs without giving you an error. And now you have to go and trace back what happened. It's very, very hard. Yeah? Do IDEs help with this? They might, but not that much. I mean, in some sense, the reason why C is this way is now C allows you to write operating systems. If you want to write an operating system, you write it in C because you actually have access to memory. If you didn't, then you wouldn't be able to do a lot of memory management. Right? Yeah. Now, let's do this one. You can also dereference I shouldn't do this, sorry. Then deref struct. So now I created the structure. I did foo bar as usual. Now I set s.id, s.major, s.year. And now I can actually create, I have a pointer to the student object. So that's over here. When you say struct student s, and you do struct student star ptrs. By the way, I should have pointed this out earlier, that in Java, if you wanted to create an object for a class, like you would just say student s. But here you have to write struct student s. Yes? No, it doesn't. The name of the pointer variable can be whatever you want. Yes? A struct cannot contain a method. So that's sort of the primary distinction between structs and classes. Structs cannot contain methods. Which is what, yeah. And typically the way you implement a method is you create another function which takes as input a pointer to the object that you're looking for. Yes? In C++ you have some object-oriented programming, so you can create methods. Yes? That's true. No, say that again. Uh-huh. Right. Right, so stylistically, yes. You might be able to do whatever you want, though. Right, so, and so you can't, yeah, but in C, there are no methods inside structs. So you don't really have object-oriented programming. You have to sort of create it in a weird way. Okay, so we have a struct student star ptrs, right? That's a pointer to a student structure. Then I go ahead and I get the address of s. And then what I can do is, so I'm actually not going to print these. I'll just print these. I can say at ptrs, what is the ID? So I dereference the pointer first. I do dot ID. I dereference, I do dot major, and then I do dereference and dot year. And so ignore the commented lines for now. And so if I run this, no warnings for a change, because all I'm doing is just printing stuff out, and then I get essentially star ptr.id, star ptrs.major, and .year as 100C in 2017, as before. Yeah? Oh, so what is GCC? That's just a C compiler. It's the GNU C compiler. Question? Yeah? I didn't get that. Say that again. Right.
So when you try to reference it, will it give you the structure?
It depends on which pointer you use, right? So actually I have an example of that. But right now in this code, ptrs is a pointer to a student. And so when you do star ptrs, it actually fetches the entire object. So that's why pointers are all just addresses, but depending on the type of the pointer, it would fetch different things. Yes?
So in the previous example, when you said PTRC didn't work, but if we
Well, it worked.
it compiled it, like it gave garbage.
Right.
If we construct another structure or struct with a different name, so like they struct teacher,
Uh-huh.
and then we create a pointer to that teacher, and we set that pointer
student. I mean, it would basically, you can manipulate pointers however you want, and the compiler will probably, it might say something, but it will let you compile. But then the interpretation of the result is going to be extremely hard, right? So when you do star ptrs, it says, the compiler says, I'm going to imagine that whatever is at location ptrs is a student object and just fetch all those contents. Maybe it's not, maybe it is, it doesn't care. And it will just go ahead and run and produce some output. I mean, I can, okay, I'll do that later. But then, so this operation here, which is dereferencing a structure and picking up a field, right? That's what happens. You dereferenced a pointer to get a structure, and then you get a field, is a very, very common operation in C. And so there's a special operator for doing this, and that is the arrow operator. And so look at this. PTRS arrow ID is the same thing as star PTRS.id. Make sense? The arrow operator is the same as doing this. You will almost never see anyone doing this. It's always this. So what this means is you look at the structure pointed to by this, and in that look at the ID field. Make sense? And if you compile this, you get basically the same struct.c. Right, which file is this? Ooh. Ah. There. Right, so this and this point the same thing. So this operator here, star ptr dot id, is the same thing as ptr arrow id. Right? So you've learned three operators, right? Ampersand, star, and arrow. Questions? Yes? No, when you have a struct pointer, as we printed out earlier, it just gives you the location of where the structure starts. So it doesn't have anything else. No, it doesn't say where it ends, because that, the compiler will say that, oh, a structure has blah number of bytes, so I'll only look at that much. Yes? Why does which? The arrow operator, or? Right. So this is not pointing to the ID. I mean, I think, okay, so don't get confused with, this is just, this over here is the same as writing this. It's just a different way of writing it. Right. This says, at the pointer s, find the ID. And that, this is a shorthand, or this is an alternate notation. You can write either of those, but you will almost always see code written with arrows. Because this is extremely common when you pass an object or pass a struct as a, by reference. So then there's another function that takes the reference and then needs to access the fields, and it just does the arrow operator. Someone else had their hand up somewhere. Okay. Yes? If you did ptrs is equal to ptr foo, you will probably get garbage, yeah. I mean, you can try it, yeah, but yeah. So how is a struct allocated? So like over here, you have 3 fields. And so it, let's see if I, so when you say student S, it has to basically block off a portion of memory for these 3 fields. Now within that, the compiler might optimize in various ways on how to align things. And so in this case, it'll put the ID here, the major here, and the year here. And again, as we said, no, it might be the case that it actually does this. It does major here, and then leaves some empty space, and then puts the year. And that's for alignment reasons. I mean, getting into that would be getting into a lot of compiler stuff, which let's leave for now. Yeah? Yes, it does. Well, invariably, as I think we have an example here where we did that. Yeah. OK, so let's look at I think this is actually one of the questions that some of you had. Maybe this will answer. I keep. Yeah, OK, so now I did basically the same thing, except now I do I take pointer foo, which is a pointer to an int, and I make pointer foo equal to ptrs. So I took a pointer to an int, and I made that equal to a pointer to the structure. And as we said, no, this code compiles. And interestingly enough, here, what do you think it'll give? Yeah? Give you garbage. Yes? Value of ID. You're going to say the same thing. Same thing. So it's going to give you garbage, or it's actually going to give you the value of ID. So let's see. It complained, but it didn't stop me from doing anything. And I actually just got the value of ID. I didn't get garbage. Why? So it goes back to someone else had their hand up. Yes?
Does it, because ID has the same address as the student, so when you call ID or address the student, you call back address of the.
Right, so this is, I guess we can also maybe make this more explicit by doing the following. So let's actually print the pointer s. Just do it as unsigned. And I'll print pointer s. But let me also go ahead and print the location of s.id. And that would be ampersand s.id. Right? Just make this. Note that the pointer s, that's the pointer to the student, is the same as the location of s.id. Right? And that's because student was allocated in this way. It was ID, major, and year, and the initial starting address is the address of student. It also happens to be the address of this int. So when you have a pointer to an int, it interprets that as an int. Back, yeah. Well, it does put gaps for alignment. But aside from that, I mean, probably. Yeah, most probably. This is all happening at the compiler level. And the compiler then will decide, once it decides something, every single struct will have the same, every single student structure will have the same structure, will have the same alignment. Yes? If you put major first, you would get garbage.
If you wanted to get the year, could you put PTR or PTR.id? Would that work if you put, or not PTR.id, PTR dot year? You said PTR foo equal to PTR s.
Yes, okay, yeah, I see. No. You would have to find out what is the location of year, and the location of year is not the starting location, it's something else. So probably if you add 8 to it, you would get it. You would have to know exactly what to add. You can't figure that stuff out, and I'll show you more commands to do that. Yes? Can you assign values in the structure? Doing, what do you mean? I just... I did. Yeah. Over here? Yeah, you could probably put, I think you can put default values. You should check, though. I think you can. Yes? If I changed what? Doing this, you mean? What should happen? It will actually change that. Right now it's 101 because you changed what's there in the location. Again, if I haven't emphasized this enough, this is why pointers are dangerous. Right? Because you can get a pointer for one type, cast it as something a different type, assign something over there, and then you're stuck with all kinds of bizarre errors. So this is sort of interesting, and I think I'll probably, yeah, let's look at this example. I keep opening it the wrong window. Okay, so same, we have student, all the pointers. Now what I did was I said PTRC was equal to PTRS. Right? So I took a pointer to a character, and I put PTRS. So what do you think I should get? Okay. It didn't like that. I actually got the letter D. But now here's something really interesting. I'm going to change s.id. Run this again. Now I got the letter E. It's actually reading, it's 101 is the ASCII value for the character E. So it's reading that as ASCII. It's even more interesting. So this is, okay, it's sort of off topic, but it's interesting. Because I looked at this and I said, wait, why is that happening? And then I had to, so there's a difference between what's called big endian and little endian in storing ints. So the way it works is the following. So remember we have ID here, major here, and year. Now this is actually 4 bytes. So let me just blow this up a bit. Right? So ID is 4 bytes. The least significant bit actually is here. So when you put 100, 100 is over here, not over here. It actually starts writing the number sort of in opposite direction. So actually 100 is in the first byte. And so when we did this, it interprets this as a character, and that character by ASCII happens to be D. And you put 101, you get E. If you put anything above 127, which is actually the limit of care, like let's say you put 150, it says, I don't know what that is. It puts a question mark. So question mark is some ASCII, yeah? So even if you start changing it, it doesn't seem to make a difference. Still gives a question mark. So I think when it exceeds 127, it gives up. And 127, that would be exact 7 bits. So anyway, so this, if you start mucking with it, you'll really get into sort of what is interpreted as what at the compiler and the machine level. You don't need to know this. I'm not going to ask you questions like this in the midterm. Or if you really annoy me, I will. So, yes? So no, it goes beyond that, but I think character is not interpreted beyond that. That's my guess. Because if you put something smaller, like you put like 30, you'll start getting something. Oh, you didn't get. I think maybe the first so many don't give you anything, and then after that you start. It could also be, yeah, I think 79 might be 0. It could also be how character is actually implemented. So, so be careful when you use pointers. That's the main thing. So maybe for the last thing for today I will introduce another operator, which is called size off. So what you can actually ask for, the size of operator, if you give it a type, tells you how many bytes that type is. So let's just run that. So didn't like that, but okay. So it says over here, the size of int is 4 and the size of character is 1. Not surprisingly, right? But this is extremely useful, and as you see this in actually dynamic memory allocation, is you can also ask for the size of a structure. So you say size of struct student. So what is the size of the structure? Because you would think that, oh, it has 2 ints and a character, and so it should be 9 bytes. But as we saw, it's doing some alignment, so it's not 9 bytes. And what you, forgot to write. You get 12 bytes. So whenever you create a structure, you use size of. So this is also like, it's like a built-in function in C. Size of any type. So you do size of struct student. Remember, it's not like Java where you just refer to the type. You always have to put struct and then the type. And you get 12 bytes. Because it's doing some alignment internally. Yes? Well, structures are not dynamically allocated. This is not dynamic allocation yet. Not yet, no. Dynamic allocation is done explicitly when you say, give me 10 bytes of memory. That's dynamic allocation. So right now, this is just saying, how many bytes do you need for a struct, for a student? And it's not 9, but 12, because that's the way the compiler is structuring things. Because it puts this, it basically has like this sort of empty space that it puts for alignment. Now, it's important that you know this because, like, next class we'll talk about how do you actually allocate memory for an array of structs. So you need to know the size of every struct so that you can allocate memory appropriately. And you need this operator. Now, what can be really confusing is this command that I have over here, which I say size of star, and I actually give it a pointer to student. I would have thought that this means what is the size of that pointer? It's not. It's the size of the type that that pointer points to. Okay, so this is quite confusing. But it says 12 because PTR underscore S is a pointer to a student, and size of star PTRS says what is the size of, the sort of the struct or the type that is pointed to by this pointer. I didn't dereference. This is not a dereference. This is a specific notation in C. This is not a dereference. I mean, okay, it is, well, that's one way of, sorry, I take that back. It is a dereference. It is a dereference. But in some sense, you didn't really give it a type. You only dereferenced a pointer. Yes? For here? We can put it in and see what happens. I suspect it will just be the same thing. Yeah, it's the same thing. So you can put that. I take that back. It is basically like a dereference, and then you say what's the size of that object or that struct. Yes.
So does the pointer store the size of the thing it's referencing?
No, the pointer does not store the size. No, this is done at the compiler level because the compiler knows PTRS is a point. Yeah, so it's not a runtime thing. Question? This? Let's see if it's 8. So it's an 8-byte. So it's basically saying you can also put the size of, I believe, S. Yeah, okay. So I stand corrected. Yeah, it basically, you can think of this as the size of that variable. And so star PTR would have been a dereference, and it gives you the size of the variable. Again, this is kind of confusing because sometimes you pass it a type, sometimes you pass it a variable. But it's useful to know that these are different ways of doing it. In your lab, I think you might want to stick to passing a type just because you know what's going on. But both of these work. Well, I guess you're ready to leave, so we're done.